Hi guys, welcome back. And I think I left you guys with a question last time. The question was to compute the average. So we are looking at a sphere of radius r. Apologies. And here's a sphere of radius r, or at least my attempt to depict such a thing in 2 dimensions. So that's the y-axis, the x-axis, and the z-axis. And we will imagine this is a sphere of radius r, and I wish to consider the average of the function d squared, okay? Where d of x, y, and z is the distance from the point located at xyz to the origin. Okay. And that's, okay, so we need to consider the average of d squared, and we recognize that d is, by Pythagoras' theorem, well, I will just make it a little more general. It's x minus x0. So, well, I'm not going to write it that generally. D of xyz is equal to the square root of x squared plus y squared plus z squared. Okay? And what I want to emphasize here is that, of course, this is d from the distance from the point to the origin, but you can go point to another point, right? You could have an arbitrary point at xyz to some fixed point, right? How far am I to you now? And then how about now? And then how about now? So you would have parameters in there. So I wonder how many people went and computed it. I asked you guys to go compute it. Remember that the average of any function is, I want you to think about this, the integral of the function divided by the integral of the number 1. Or put differently, the integral of the function with respect to the measure of the space we're considering. So when we're considering the volume average of a function, it's the volume integral of the function divided by the total volume. If the function's in 2 dimensions, this would be integral with respect to a. In 1 dimension, it's integral with respect to x. And we're about to study, in a few minutes, ideally today, we will study what we mean by mass-weighted averages also. Okay, when we'll do a study center of mass. Okay, so the function that I wish to average is d squared. So I say the average of d squared is simply equal to the triple integral over the domain of d squared of x, y, z, integrated with respect to the volume divided by the total volume. Now, we're working in Cartesian coordinates in R3. Working in Cartesian coordinates in R3. Sorry, let me see if this works. Is that a little better if I do that? So I am going to represent my volume, dV, as d. Well, I'm going to do Fubini's theorem and triple integral at the same time. So I'm going to do, the volume integral is actually going to be 3 iterated integrals. And I'm going to do the z first, and then I'll do dx, dy. And so what I have to recognize is I have to figure out what my z top and z bottom is. And I need to figure out z top of xyz. No, z top of xy, z bot of xy. That's a surface. That is one constraint. That'll be a function. That'll be a function of only an xy. And it says your top value is a function of x and y. Okay? So that would be a z up there. I'm emphasizing this because some people are getting confused between what defines the boundary of this domain, which is a surface, which is one function of 2 variables, versus possible functions on the domain, which is a function of 3 variables, right? What is your temperature as you move around? You give me x, y, and z location. I give you a temperature. What is the height of this surface? You give me the x, y location, and I'll give you its z height. Okay? So make that distinction. Understand the difference between the function you're integrating and the surfaces which describe the boundary of that function. So first we have to figure what z top and z bottom are. And then I'll do dx and the x top and x bottom next. Okay? So how do we do that? Well, we recognize the equation for the boundary of a sphere is x squared plus y squared plus z squared is equal to the radius squared. So this is one condition on 3 variables. R is a number. You give that number, okay? And of course, you can see that if you were to do the all-time, easiest way to do this problem, which is pierce the, so you go from lower z, you pierce up through the boundary. You hit z bottom first, and then you pierce up to z top. At a constant x and y, you do these vertical piercings. You see that what you encounter the sphere at the bottom and the sphere at the top. And if I want to write z, solve this equation for z, what you have is r squared minus x squared plus y squared, all square rooted. And of course, you have the positive and negative square roots. And especially in this case, it's pretty clear that the positive square root is z top and the negative square root is z bottom. I'm doing this to help erase the board. Okay. Now, let me write my numerator. The numerator is equal to the double integral over the domain in x, y. Well, let me just, I'll write the integral from x0 to x1, from y0 of x to y1 of x, where this is the top and this is the bottom in x. Then we're going to do the z integral. So z bottom is going to be the negative square root of r squared minus x squared plus y squared, all the way to the positive square root of r squared minus x squared plus y squared. And what you have to integrate is x squared plus y squared plus z squared with respect to z, and then you have to do the integral with respect to x and y next. And so it should be the y integral next and the x integral last. So I did it wrong up there. That should be dz, dy, dx. Okay, so I chose that ordering. That's the numerator. Now, folks, if you want to find the denominator, you would perform same boundary of integration, right? That's the thing. When you get the boundary of integration, it's the same boundary of integration. That's the hard part, is getting the boundary of integration. The only difference is you wouldn't have a function in here. It was just the number 1. Okay? But of course, you have a function here. And I hope you'll allow me the understanding that the volume of a sphere, we already know what it is. So you could go about doing the integral, or we could skip it because you're getting sick of me doing integrals. You want to see something cool, right? You want to see something more cool than integrals. And I don't blame you, because I want to do something more cool than integrals. So we're just going to write out what the volume is 4 pi r, 4/3 pi r cubed. 4/3 pi r cubed. Okay. Now I integrate. So notice, by the way, there's a reason. You'll see the reason in a second. Okay. I was lazy. Okay. I did not tell you what the boundaries in x and y are yet, but I know there's got to be some sort of boundaries. Okay. So let me do this integral first, and then let me talk about the boundaries in x and y. So when I do this integral, the integral, this has got two parts, x squared plus y squared, and it's got z squared. So when I integrate x squared plus y squared over this, well, when you take the antiderivative of x squared plus y squared with respect to z, you're left with x squared plus y squared times z, because this is constant. And of course, when you integrate z squared, you're going to get z cubed over 3. And all of this has to be evaluated at negative square root of r squared minus x squared plus y squared to the positive square root of r squared minus x squared plus y squared. Okay? That's the evaluation of all of this. And then you have to do dy dx after that. So I will continue here. We know, I should remember what the volume of a sphere is after I've erased it. I think I'll be OK with that. So I continue, and I'm left with the integral just x0, x1, y0 of x, y1 of x. Okay. And now we just have to evaluate all of this. Well, the first term is x squared plus y squared times this minus this. Okay? Because I'm evaluating it z upper, just looking at that first term, z upper minus z lower. Well, this minus this minus negative itself is just twice itself. Okay? So really what I have here is 2 times the square root of r squared minus x squared plus y squared. That's the first term right over here. Okay? And by the way, this is clearly an example of a symmetric function. The symmetric function is the function z equals 1 integrated over a symmetric domain. Because I got that factor of 2, because this domain was symmetric. So you always have this minus negative this if you had the symmetric domain of a symmetric function. Okay? This is a symmetric function also, z squared, and the antiderivative z cubed, and you can evaluate this cubed minus this cubed. But of course, with the negative, it's minus negative again. Okay? So if I write that out, I'll have plus 1/3 of that radical cubed. So that's cubed, and there, of course, there's a square root over there. So I'll just write it to the power of 3/2. Okay? And this is then dy, and this is dx. Yes?
If we're given a fairly common shape like a sphere or a cube, are we allowed to use the just normal formula for volume rather than the triple integral?
If you are given a common shape, you are absolutely encouraged to do that. Okay? You're absolutely encouraged to do that. Because I will give questions like, that'll have multi-steps to them. And it is OK to use your knowledge of the volume of the sphere, unless I say explicitly, you must find the volume of the sphere this way. I don't like to do that. I don't like to tell you how to do things. I really don't, right? You know things, go show me that you know them, right? You know the volume of the sphere, boom. Okay? So yeah, no, you write them down, okay? Because it'll be the numerator integral. So if you can minimize the number of integrations you have to do, that's fine, because what I really care about is what integrations you have to do, okay? That's much more important to me. Yes? Oh, sorry. Oh, we had two in a row. I was going for her first, then you next.
Because you do.
Yes, you are correct. That was the 2. I talked about 2. I blah, blah, blah about 2, and then I forgot about 2. You may shake your heads disapprovingly. Or shake your fists disapprovingly. Thank you. Was that the same point you were going to make? You were nodding after I said, yeah. OK, we're good. 2/3, thanks. OK, then I got to do this integral. Now, the point is, we have to figure out y min and y max, OK? Look at the sphere. Go above the sphere at maximum z, look down, and what you see is the sphere from above occupies a space in R2, right? It covers the xy space, which is a disk of radius r, okay? What is happening there? Well, the boundary, right, the y max occurs where where z top intersects z bottom. That's what's happening. That's where y max is, right? That's the curve. So it's not the curve. It's not just y max. That's the curve that describes the boundary of the shape in the xy space. Okay? So where does z top of xy, which equals the square root of r squared minus x squared plus y squared, that's the top surface, equal z bot of xy, which is equal to negative square root of r squared minus x squared plus y squared. Well, this is a number. Oh, sorry, this is a number. This is its negative. Where does a number equal its negative? When that number is 0. Right? I mean, it's obvious geometrically, but if you ever came up to a place where it wasn't obvious, right, you're like, oh, it's where this thing equals, where each of these equals 0. Therefore, z equals 0 on this intersection. That's nice to know. That's where that curve lives. But you care about its xy values, and r squared is equal to x squared plus y squared there. Right? Which is that circle that I told you about in the xy plane. That is to say, to make this everything in the radical 0, well, just make it 0, 7, you got that. Okay? Good? So, we can go about and do this with Cartesian coordinates, but why? So if you come to a point like this and you're like, I started with Cartesian, wait a moment. I don't have to keep killing myself and doing Cartesian on this one. I can go polar, so go polar. Go polar. I don't know. I amuse myself with these random little, now it's a new saying. Go polar. Okay. This is the integral. Interpret this integral, right? This is the integral over the disk of radius r. That's what we mean by this integral. I haven't said it explicitly, but that's what this thing has collapsed to. Looking from above, you're occupying the disk of radius r, right? So you need to get the boundaries of this in polar. So first note, 1, dy dx is equal to r dr d theta if you go polar, right? Or put differently, maybe I should add a step. dy dx is equal to dA. It's the area element in the xy plane, which is represented as r dr d theta. Okay? That's the important thing. That's the area element, and that's its representation in polar coordinates. 2, okay? Part 2 is look at the boundary. Look at boundary in r theta. And I tell you, everybody, I mean, when we use the polar coordinates or the other, when we use polar coordinates, I am not generally interested in testing you on figuring out what complicated shape the boundary is. I'm generally going to give you straightforward boundaries, especially on an exam, on a midterm or a final, okay? The boundaries here are very, very straightforward. It's the disk, okay? So in the xy plane, this is the xy plane, we have a disk of radius capital R, that's capital R. And so you do your shooting method, et cetera, but I hope you've got adept enough now that you realize this has theta min is equal to 0, theta max is equal to 2 pi, r min of theta is equal to 0, and r max of theta is equal to capital R. We've done examples over the disk. So now all we have done is we have to integrate this somewhat complicated function over the disk of radius 1. The disk of radius 1 is super, super easy to represent in polar coordinates. That's why you use polar coordinates. Okay. Wherever I see x squared plus y squared, I put, what do I replace it with? R squared, little r. Little r is the variable. Capital R is some number that I'm not telling you what it is, okay? So this becomes equal to the integral from 0 to 2 pi, the integral from 0 to capital R. X squared plus y squared is little r squared times the square root of big R squared minus little r squared. That's that first term over there. I think I forgot the factor of 2 again. Okay? And then it should be a plus 2/3. The square root of, no, that's not right, it's square roots. R squared minus little r squared to the power of 3/2. And then I have to integrate this r dr d theta. So I have to do that integral. Now here's trick number 1. Trick? No, not trick. Observation, wisdom. Right? Tricks are just a mean way of saying wisdom. After doing this often, you see certain patterns arise. Notice that everything in here does not depend on theta. Neither the function nor the bounds of integration. So in essence, I can just quickly switch the order of integration, do the theta integration first. Because nothing depends on theta. And the theta integration is easy. It's going to give me a 2 pi. When you have circular symmetry, 2 pi comes out all the time. So look for it. Get it out of your way if you can. So I got a 2 pi from this integration. So now I'm skipping a step. Flip the order, do the integration, and then I'm left with 4 pi from the 2 here and the 2 pi there. The integral from 0 to capital R of r squared, and I'm going to write this as r squared minus little r squared to the power of 1/2 plus 2/3, no, 1/3, because I factored out the 2 this time. You didn't like it. I see a hand looking, what the heck? What did you just do? Okay, I see your hand. I will acknowledge it in a second, and we'll see what I just did. It was your hand. I saw you go. I got the. Explain that to me, hand. Okay, yeah, you're keeping track of my 2 for me today, because I can't do it. Okay, so 2 pi from this end, and then 2 from there. Okay. Now I got to do this integral, and you know, even me in my old age, I start to get very scared of like, oh, square roots. I got to do the square roots. I don't know what I'm going to do. But we can deal. We're strong people now. Okay. I tell myself that. That's how I get through my day. I'm strong. I can do this. Okay. This is screaming out for a U substitution, okay? Screaming for it. What's my U substitution going to be? Well, you could do a lot of different U substitutions. I can see substituting r squared. Okay? I can see substituting r squared first. Okay? Or I could see substituting r squared minus r squared. Okay? That could be a useful U substitution also. So allow me to let U equal r squared minus little r, capital R squared minus little r squared. So that'll come up a bunch in these kinds of symmetric problems. So I'm going to let U equal capital R squared minus little r squared. That means du, and this is crucial. This is crucial. Du is going to be negative 2. That's not the crucial part. That's the crucial part, RDR. The point is this RDR over here, naturally, very effectively, is eliminated by a substitution which is proportional to r squared. Okay? So when you see it, you think, OK, an r squared type of substitution is useful. And there's the little r squared right there. So that means I'm going to eliminate that RDR in favor of du over negative 2. So this, therefore, r squared, no, I did that at the beginning, so don't worry about that. Therefore, little r squared is equal to, because I have to eliminate little r squared also, little r squared is equal to capital R squared minus u. Okay, because that's one of the terms I'm going to have to eliminate. And then when you do a U substitution, you say when r equals 0, which is the lower bound of integration, comma, u is equal to capital R squared. When r is equal to capital R, u is equal to 0. So that affects the whole transformation. So with that, I've made the whole transformation. And so the integral, we're still working on the numerator. I should have a 4 pi. That's interesting. I should have the integral. Well, the lower bound now is r squared. The upper bound is 0, just by looking at that. Okay? Now, r squared is replaced by capital R squared minus u. That's the first term. And the second term is simply u to the 1/2. So this is just u to the 1/2 right there. And then the last term has a 1/3. And that should be u to the power of 3/2, apparently. And RdR gets replaced with du divided by -2. Okay? And by the way, you see that this negative is going to switch the order of integration. This is what tends to happen, right? So it's going to go back to the other order of integration. Okay? So I'm going to have 2 pi times the integral from 0 to r squared of r squared u to the 1/2. I'm just expanding now. Minus u to the 3/2. That's u to the 3/2 over here. Plus 1/3 u to the 3/2. So by expanding it, I'm going to save myself one integration step. And then I integrate that with respect to u. And so this is going to be equal to 2 pi times the integral from 0 to r squared. That's the bounds of integration. R squared u to the 1/2. That's the first term. And the second term, I get a -1 and a plus 1/3, so it's a -2/3. -2/3. U to the power of 3/2. And if anybody sees any algebraic error, please stop me now. Good? I could be wrong. I make algebraic errors, okay? But the essence of this calculation is correct. I am certain. The integral of u to the 1/2 is u to the 3/2 times 2/3. The integral of u to the 3/2 is u to the 5/2 times 2/5. Right? I made a mistake again?
You dropped an R. A capital R.
This is up here, you mean? Oh, here, this one. Is that the only one you wanted me to tell me what else? At least slows me down. So I got the r, yeah, this is an r squared, so there should be an r squared here. There's the u, there's the u. I think I'm good. Again, I don't promise you anything. There are no guarantees in calculus. That's not true. There should be some guarantees. Okay. Are we okay with this? So this is going to be 2 pi. Let's see what we got here. U to the power of 3/2 evaluated r squared, and u to the power of 3/2 evaluated 0. Well, the lower bound is 0. That's not interesting. So we're going to have 2/3 r squared from here. And this is going to be r squared to the 3/2, which is simply r cubed. R cubed. 2/3 r squared r cubed minus 4/15 r to the power of 5. And this is interesting, and this is important, and I hope you see why I retain units. R is a length. I cannot, so I'm taking it to the power of 5 in the first term and to the power of 5 in the second term. That's the only way I could subtract them, or else I wouldn't be able to subtract them if they had different powers, right? One would be length to the 5th, and the other one would be length to the 4th or something. So then I'm left with 2 pi r to the 5th, and 2/3 is also equal to 10/15. Is that correct? 10/15 minus 4/15 is 6/15. Okay? So this is going to be 6/15, which is 2/5. So I don't claim that I'm 100% correct, but I'm pretty sure that 2/3 minus 4/15 is 2/5. This is how bad I am these days, guys. 3 times 2 and 3 times 5. Yeah, that's correct. Okay? Now that's the numerator of the average. That's the numerator of the average. Okay? So recall, this has units length to the fifth. As well it should, because it was a length squared integrated with respect to a volume. So it better have units length to the fifth, because I'm about to divide it by the volume. So d squared average is going to be equal to 2 pi, the radius of this object to the power of 5, times 2/5. So I'm keeping 2/5 along for the ride, divided by 4 pi r cubed over 3, which is the volume of the sphere. So notice the first thing that happens is we have r squared in the numerator. Right? R to the fifth over r cubed is r squared. That's good. I've got 4 pi here and 4 pi here. They're going to cancel. And I'm going to be left with 3/5. So the distance squared is 3/5 the radius squared. So does that have any meaning to you? It really probably doesn't have a deep meaning to you, right? It doesn't have a deep meaning to you, but what do you mean by the distance squared? And I think I asked you guys to compare this to the cube. Did anybody do the cube? Excuse me. Is everybody okay? So, huh?
Because we're doing the average of the distance squared, that's why it turned out to be r squared rather than just capital R, correct?
Absolutely. Yes. Absolutely. Great. Yes. Totally. It's because we're using a distance. We're averaging d squared. We have to get an r squared. If we were averaging d, it would be something proportional to r. It'd have to be proportional to r. So this is proportional to r squared. And really what this measures, guys, is sort of an effective extent of this sphere. You think about it, like the stuff is really concentrated in the center. There's a lot more stuff in the center and further out. You're like, what do you mean it's measuring an effective extent? Well, what if you were to just take the square root of this, the average? It's called the root mean squared in statistics. Okay? So d squared average to the power of 1/2. Well, that's clearly a length. And so that's equal to the square root of 3/5 times the radius. Okay? So the square root of 3/5 is the square root of 0.6, which is, I don't know, what's the square root of 0.6? It's 0.8? It's like 0.8 squared, it's like 0.7 something. 0.8 times 0.8 is 0.6. 4, it's 0.64, so it's about a little less than 0.8. So it's maybe about, 0.78 times the radius. So this is about 0.78 times the radius. So it tells you something about the extent of this object. Okay? It tells you something about the extent of this object. Did anybody do the cube? I'd asked you to do the cube. Nobody did the cube. Well, you're going to suffer this. Okay? You're going to see me keep talking. You could have shut me up like that. But no. What would the cube give us? Okay, let's say I did all of this calculation for the cube. It's not going to take that long for the cube. Okay, it's not going to take that long for the cube. You ready? So we're going to have a cube centered on, okay, it's going to be centered on the origin. Let's center the cube on the origin, like that sphere was centered on the origin. And it's going to have side length r, capital R, to negative capital R. So it's going to have side length 2r, okay? So we know what the volume of this cube is. You do not have to do integrals to the volume of this cube. It's going to be 2r quantity cubed, which is 8r cubed. 8r cubed, okay? And by the way, I want to compare that to the volume of the sphere. So this is the volume of the cube. And this is the volume of the sphere, which is 4 pi over 3r cubed. So if you were to give me a rough estimate, what's the volume of the cube compared to the volume of the sphere? So the sphere that sits right in that cube, right? It's the sphere that goes right up to the cube. Twice, about twice. Somebody said 2. 4 pi, pi is about equal to 3, right? So this is a little more than 4. The result of this is a little more than 4. Okay? Pi is about 3 1/7. So this is 4 4/7. So 4.5. This is 4.5 and this is 8. So it's maybe not double, but getting there. Okay? And it's not the volume of the cubs, it's the volume of the cube. And then I want to calculate, and we know that the, let's just say the d squared average to the 1/2 is approximately equal to 0.78 times the radius. That's sort of measured the extent for the sphere. What does it tell us for the cube? Well, I have to do all those integrals again for the cube. But they're a lot easier because the boundaries of the cube are super, super easy now. So let's consider d, so the numerator is equal to the integral from negative r to r, the integral from negative r to r, the integral from negative r to r, that's the boundaries of a cube, of x squared plus y squared plus z squared times, well, I'll do dz, dy, dx here. I'm just going to do it. I don't even know what the answer is, but I'm curious now. So because of my curiosity. Now, the first thing I want to point out to you is that this is a symmetric function over a symmetric domain. Symmetric function over symmetric domain, symmetric function over symmetric domain. I should be able to, I realize that I can double the value and put the lower bound to be 0. So this is going to be 2 times 2 from here times 2 from here of the integral from 0 to r, the integral from 0 to r, the integral from 0 to r of x squared plus y squared plus z squared dx, dy, dz. So there's a, you see my factor of 8 right there. Okay, it's coming out right out of the wash right at the beginning. So this is going to be equal to 8 times the integral from 0 to r, the integral from 0 to r. I'm doing, sorry, let me do the z integration first because that's what I said I would do, and the x integration last because that's what I said I would do. And so what we're left with is x squared plus y squared z plus z cubed over 3. Similar kind of thing. Evaluated at z equals 0 and r, and then I have to do the y and the x integration. So this is going to be 8 times the integral from 0 to r, the integral from 0 to r, of x squared plus y squared times r plus r cubed over 3. And then I have to do the y integration, and then I have to do the x integration. And the y integration is going to give us x squared y plus y cubed over 3 all times r plus r cubed y over 3, all evaluated at r equals 0 and r equals r. And then I have to integrate that with respect to x. Okay? Breathe, breathe. Okay, here we go. 8 times the integral from 0 to r. That first term is x squared r squared. Right? Because x squared r and r. So that's x squared r squared. So x squared r squared in the first integral. This is going to be r to the 4th over 3. And this should be r to the 4th over 3. And then I have to integrate that with respect to x. You wouldn't have suffered this had you done that, what I'd asked. You have to suffer me going through this crazy fast. This is 8 times x cubed over 3 r squared plus 2/3 r to the 4th times x, all evaluated at x equals 0 and x equals r. Okay? This calculation is trivial, right? It's just a bunch of little trivial integrals. But let's see what it gives us. Because I don't care right now. I actually do care about the answer. It's the thing that I care about the most. Because I want to compare it to what I just got for the sphere. So this is 8. And this is going to be r to the 5th. And this is r to the 5th. That's cool. And it looks like I've got 1. 1/3 plus 1/3. So this is for the sphere. And what do I have to do? I have to take that numerator there and divide by the volume of the cube. And so if I do d squared for the cube, that's just equal to r squared. Or that implies, this is for the cube, or that tells you that d squared averaged to the power of 1/2 is just equal to r. So now you've got something to compare it to, and now you've got this new thing that I asked you to calculate, which is the average of distance squared. You're like, what does that tell me? What do I care about that geometrically? Well, look, for a cube, the average of the distance squared is actually the side length. Okay? It's the side length. For a sphere, it's less than the side length. It's 0.78 times the side length. So, oh, it's sort of measuring the compactness of this thing. It's measuring the compactness of this thing. The cube is more extended for an object of the same horizontal extent. So it's a way to compare these two objects. If I did that calculation correctly. So that's why I always keep units, because here you can compare a cube with a comparable sphere. And why am I doing this? I'm doing this because I had intended to get into center of mass today, density, and centroid, and moment of inertia. And when I was your age, we were taught about moment of inertia in mechanics classes. And for me, it was just this calculation that I was told to do. Here's this calculation. And I asked, why does it come out that way? What are we really measuring by the moment of inertia? Okay? What is the actual thing that's being measured? That I hope, as we will go forward, and I will explain in more detail, but I hope this kind of discussion contextualizes what we're going to measure, what it measures. Okay? Are you guys okay? I feel like a train hit my class. Yeah. Go ahead. So the average of d squared is just the average of the distance squared at every point from the origin. Okay? So you think about, it measures the average distance squared. It measures this quantity. Right? So you can average anything you want, right? You can average anything you want. And you can imagine averaging distance squared because, oh, that's an easy quantity to compute. But what does it give me? Well, if your distance is very small, right, it has a lot less effect than if your distance is very large, right? So if your distance is 1, distance squared is 1. If your distance is 10, distance squared is 100. So it really emphasizes things that are extended outward, okay? Yes?
Why didn't we do the z integration of the sphere in polar?
In spherical polar? Why did we do polar at the beginning?
Yeah.
Because I haven't introduced cylindrical coordinates yet. Because what we really just did was cylindrical coordinates. Okay, so what I did was cylindrical coordinates. Yes, completely agree. But what I was trying to show you is you choose cylindrical coordinates because it makes things easier. So I haven't talked about cylindrical coordinates yet. And that's after we talk about center of mass. We need to do an application now. So that's we don't need to, but I think to keep the class awake, I should do an application or else they're going to fall asleep. Okay? But getting back to your question, what is this thing, right? So this measures an effective size. D squared is not a length, but the average of d squared is some sort of average length squared. And the square root of that is a length, some sort of averaging of a length. Okay? Now, if you imagine what you want to measure, well, when you take an object, an extended object, what do we do so where does this go? Let me just tell you where this is all going, guys. In mechanics, one of the things they say is, imagine a point object and forces on this point. And we used to accept that, like, okay, I put a force diagram and I'm pushing a piece of chalk up an inclined plane, but the chalk has to be infinitesimally small, right? We don't actually push point objects. We push objects that have some extent, okay? We push objects that have some extent. So, but we have a notion, you and I, about what the center of this object is. Okay? We have the notion about what the center of the object is. Okay? So we're going to define the center of the object, and we're going to also define what's going to be the center of mass. Okay? And those are two different concepts. The center of the object only cares about the geometry of the object, what I can see from the outside, its boundary. But the center of mass has to take into account some properties. This is an eraser. This stuff is less dense than the back. Right? So the center of mass is going to be further to this side because there's more stuff to the right. Okay? And that's important in mechanics because Newton's law weights the mass more importantly. Right? F equals ma. So we need to know where the m is. Now you look at this object and you say, okay, this is an object that is long, right? And now your brain might have a different shaped object. Maybe it looks like an egg like this, right? And you would say to yourself, oh, they're about the same length, right? You have like a spear that's long and thin, and you have another long and thin stick. Maybe it's a little thicker, but you say their properties, their dynamical properties are going to be about the same. So what you want to measure is not just the location of the sphere, but something about the shape of the sphere, the extent, okay? And you want to imagine different objects with similar extent behave in the same way. And so the extent of the object tells you something about this. Watch what happens. Gravity is acting on the whole darn thing, right? But I put my counteracting force in the middle, nothing happens. Nothing happens. But if I put my counteracting force here, it not only drops, but it spins. Okay? And this is what we deal with when we deal with torque. Okay? Torque is the act of putting a force on an object away from its center, from its functional center. Okay? So I'm torquing the object by putting the force out here, okay? In this case, I'm counteracting the forces out here, okay? And so you need to know something about the extent of the object. And what the d squares measure is information about the extent of the object. And that's what I'm trying to get at, okay? And now, I have to teach you a whole mechanics class to be able to teach you that. I would gladly teach you a mechanics class. But that's the essence of what they do when they study torques, and then when we're going to describe moments of inertia. Okay? What they do, who's seen moments of inertia already in a mechanics class? So what you do, what you're really doing when you calculate moments of inertia is this. You take a look at Newton's law, and you describe Newton's law for an extended object. And what you do is you integrate. You're actually integrating over the whole object. You're taking what's called moments of Newton's law. You multiply it by constant and integrate. You multiply it by x and integrate. You multiply it by y and integrate. You multiply by y squared and integrate. Okay? And then you make one more assumption that the object cannot be broken. It's rigid. And then you go from a dynamics on the whole object to a dynamics on the object as though it's a rigid shape. But we know no object is a rigid shape. I just call this a rigid shape, but I can break it if I wanted to. Okay? But what you guys in intro mechanics don't deal with the bending and the breaking of these objects. That's more advanced mechanics. What you deal with is imagine an object is rigid. And so we have to describe the properties of that object. And down deep, and I'm going to not give you any more calculus examples. This is all motivation. We'll do center of mass and centroid on Monday. Down deep, what you care about with a rigid object is where is it? So you say where is it is defined by its center, and which way is it aligned? So you need like a direction. There's the object. So you need to know how far it's aligned in this direction, how far it's aligned in this direction, and how far it's aligned in that direction. And now you imagine, oh, I got 6 pieces of information. Its location, 3 coordinates, and its alignment. And that's why you need, well, that's what the reductions of moment of inertia are all about, okay? But I'll give you gory detail about that on Monday. And so please read the section on center of mass, centroid, moment of inertia. I'm not actually going to test too much on moment of inertia, but I probably will quiz on it. But I'm not going to test on it, okay? Because I really think it makes more sense if you have a full mechanics class. Then we'll go into coordinates, spherical coordinates. I generally skip the last section of chapter 15, which is transformations. And then I'm going to ask you guys to read chapter 13. So if you guys can read ahead, you will be happier. Have a good weekend. Please don't breathe too much smoke. I hope all your families are well.
So you just how the function